go. We're going to be talking about apparent weight today. So yesterday we talked about just weight force in general, and so we kind of used this adaptation of Newton's second law where we had F sub g equals mg, right? This is the force due to gravity, aka weight, is equal to mass times acceleration due to gravity. And near the surface of Earth, g is a constant. Okay, so if an object has a certain mass near the surface of Earth, its weight is not going to change, correct?
Yeah.
Okay. F sub g does for a given object on or near the surface of Earth, it is not going to change unless the mass changes, right?
Mm-hmm.
Okay. But what we're going to talk about today is apparent weight. Hope I spelled that right. Okay. So apparent weight is kind of what you would more or less experience, how it appears that your weight changes if you're maybe accelerating under different circumstances. Okay, so your weight is not actually going to change, but it kind of feels like it does, right? Think about like if you're falling and having kind of that feeling of weightlessness, or like in an elevator, as you're accelerating upwards or downwards, you kind of have that weird feeling, you know. That's kind of what we're going to be talking about today. So we're also going to take a look at scales. Okay. So first off, I want to talk about how scales actually work. Okay, so we can kind of understand some things here. On a scale, you've got a surface that you stand on, okay, that will be attached at some point. You know, it may have some like telescoping pieces to keep it somewhat level, but somewhere there's going to be a piece that comes down that is attached to a spring. Let me think about this for a second. So there's going to be a spring, maybe even two springs underneath the scale. Okay. And they're going to be calibrated in such a way, there's going to be a piece attached to that somehow. And basically, the further that moves, that's going to read on a dial. Or there might be some type of hinged piece here, and that's how, like the old analog, you know, now we've got digital scales, which are going to be different. But like the old analog scales, this is going to physically move a needle.
Yeah.
Okay. Now the thing about springs is springs within a certain range, you know, once you get them so stretched or so compressed, things start to kind of go haywire. But within kind of a certain range, they tend to be very linear, okay? Meaning it takes a certain amount of force to compress at a certain distance, okay? And as you increase the force, it will compress further and further and further, okay? Very linearly, which is nice for a scale, right?
Yeah.
So what happens is that if you have, say, like if I put a 10 kilogram weight on a scale, that would have a force of 98 newtons pushing down. That's going to collapse the springs a certain distance. Okay, so once it starts to collapse so far, it's going to exert more force back up until it balances out and stops, right?
Yeah.
Okay. Once if I change the weight then to 15 kilograms, well, this weight force is going to increase. That'd be what? 98 plus 49 would be 147 newtons. So now that spring is going to compress further, right? But the more it compresses, the more force it's exerting back up until it balances out. Okay? And then it's going to stop. So what I want to kind of illustrate here is with this scale, the block is exerting this weight force down, the scale under an equilibrium is going to exert an equal force back up on the block, right?
Yeah.
Because in order for it to be stationary, not move, it may kind of bounce up and down at first, as it's kind of equalizing out. Once everything stops and it's stationary in equilibrium, your free body diagram on the block would look like this. You have weight force acting downward, and then the scale, you can put SC for scale, or a lot of times they'll probably do SP for spring force, will be equal and opposite, right? Okay, that's going to help us understand what goes on with apparent weight. Okay. So, just real quick, in a normal situation, so we'll kind of go with normal, no acceleration. Okay. If you're just like standing on a set of scales, normally, like in a normal set of like bathroom scales, the scale exerts the only upward force on you, right? So if you imagine, here's the scales and my little stick person. You have this is kind of what I just did. You have their weight acting downward, the spring force acting upward. So notice the scale, these two are going to be equal, right? Okay. So it reads your actual weight. Okay, does that make sense? Now, this is kind of a hypothetical thought experiment. It seems kind of weird, but we actually, to kind of measure apparent weight, because again, like imagine being in an elevator or in free fall or these different things where you're accelerating, okay? You can feel the effect of that, right?
Yeah.
So we're gonna imagine you're actually like standing on a scale in those situations, even though you wouldn't normally do that, right?
Yeah.
So like, we're gonna talk about imagining like standing on a scale in an elevator, just so we can talk about apparent weight, even though you normally wouldn't do that. The apparent weight would still be the same, whether or not there's a scale there, okay? So, if we are in an elevator, of course, if the elevator is not accelerating, it's gonna be this. Even if the elevator is moving upward at a constant velocity. Okay, so do I need to go through that, or does that make sense? If the elevator is moving upward but at a constant velocity, there's no acceleration, the scale would still read your actual weight.
Yeah.
Okay. Same thing if it's moving downward at a constant velocity. Okay, moving upward or downward is not going to change this. If there's no acceleration, remember that's still kind of that case of equilibrium. Net force is still zero.
Yeah.
So it's that type of free body diagram. Now, as soon as we begin accelerating, things start to go wonky. So let's take a look at what happens if the elevator accelerates upward. So I'll put accelerating. Okay. So if my elevator is accelerating upward, imagine I'm still standing on this scale, what do we know about the net force?
It's decreased, right? Wait.
Okay, let me maybe phrase that in a different way. If we're accelerating upward, we know there is a net force, correct?
Oh, yeah.
Okay. And in what direction would it be?
Upward.
Okay. So, if I'm accelerating upward, can my free body diagram be balanced like it was here?
No.
No, what do we know has to change?
The up arrow has to get longer.
Yeah, if I'm accelerating upward, I know the net force is upward, right?
Yeah.
Okay, so what are these two forces respectively acting on the person?
Force of gravity is acting downward.
Okay, which that's your weight, correct? So what's this one?
Is it the elevator? Or
Yeah, so technically, but if we think about the elevator, here's the cables and stuff. Um, if we're standing on the scale, what is actually pushing the person upward?
floor?
Indirectly, but what is the contact force actually acting on the shoes of the person?
The scale.
The scale.
Okay.
Okay, so yes, the elevator is providing the upward force to start with, but it's pushing on the scales, and the scales then themselves have to push up on the person.
Alright.
Okay, so yes, it's easy to think about the elevator providing the force. That makes sense, but if we're looking at the guy as the system, what is actually putting the contact force on him?
The scale.
The scale. Okay. Okay. So what you'll notice here, did the guy's actual weight change?
No.
So what happened to the spring force?
Increase.
Mm-hmm. But just think about it. Does it make sense if you're standing on a scale in an elevator and it begins accelerating upward, that due to that additional upward force accelerating, that's going to actually make the scale read heavier? Okay? That spring force increased. Okay? So scale reads heavier. Okay? Yeah, so I'm trying to think about any additional way to explain that, but yeah, that additional force that's accelerating has to come from what's pushing up on you, and that's actually the spring. So yeah, you can imagine if that's your, I don't know, it just seems kind of intuitive to me. As you're accelerating upwards, you feel heavier, right?
Yeah.
You can kind of feel the floor pushing up on you. Okay? So you are accelerating upward. And again, this would be the same case even if you weren't standing on a scale. We haven't talked a lot about the normal force yet, but normally we can just replace, if you're standing on the floor of the elevator, we can replace the spring force with the normal force just from the floor. Okay. Normally, your weight acts down, the floor is going to push back up, equal and opposite. When you're accelerating upward, the floor is exerting a greater force than your weight. Okay. What about accelerating downward?
We're gonna feel lighter.
Yep. Okay. So yeah, I mean, I think we can kind of process elimination here. If you're heavier accelerating upward, you're going to feel lighter when you're accelerating downwards. What would the free body diagram look like here?
Be two arrows going downward. Right.
Does the weight change?
No.
Like the actual weight does not. Okay. The net force is going to be downward, right? Because if I'm accelerating downward, the net force has to be downward. The other arrow is not necessary. The spring force is not actually acting down. It's just less.
Oh. Yeah.
than F sub G. Okay, which is what causes you to be reading a lighter weight. Okay, so yeah, the net force is downward, so it's not balanced. Your weight is actually greater, and this will cause the scale to read lighter. Okay. Does that make sense?
Mm-hmm.
All right. Okay, now this I think is pretty logical. Um, the thing that might make this a little bit more confusing is that there's a couple different scenarios that each of these things can happen in. Okay, so for example, this no acceleration, that can happen if the elevator is completely at rest, right? It can also happen when the elevator is moving upward at a constant velocity.
Yeah.
Okay, no acceleration, no net force. Okay, it can also happen if the elevator is moving downward at a constant velocity. Again, no acceleration, no net force. The direction of movement really is irrelevant for these. Okay, that's kind of a big misconception. We want to think moving upward, heavier, downward, light. That's not true. The direction of movement is irrelevant. It's
The
all about bingo. It's all about the acceleration.
Because if you were going down and then it accelerated upward to slow down,
Right.
it'd feel heavier.
Yep. So let's go through a couple of those cases. Yeah. So if let's say this is hard to draw, but if your elevator is moving downward, and then you're getting, like, say, to the first floor, okay? And so you're moving downward at a constant velocity, and then you begin slowing down to stop.
The acceleration would be going upward.
The acceleration is upward, which would mean the apparent weight would be heavier, okay? If we're going upward, like say we're going to like the 5th floor, moving at a constant velocity, and then we get close to the 5th floor, we begin slowing down.
Acceleration would be downward and you'd feel lighter.
Right, you can kind of imagine you're going up and then you start slowing down, you kind of have that where you feel like your stomach kind of rises a little bit, and it's like, okay, yeah. Then, let's imagine, okay, I'm at the ground floor, so I'm stationary. Okay, everybody loads into the elevator, and then we begin accelerating upward to go to whatever floor.
Heavier.
Yep, your acceleration's upward. Your apparent weight's gonna be greater. Okay, so yeah, there's two different kind of cases. You can imagine, from whatever floor to whatever floor. Let's kind of go through the whole range. So my elevator's stationary at first, just normal weight. As it begins accelerating upward, kind of during this time frame, it's going to read heavier, right? And then let's imagine, so I'm going to try to make my dots there to show acceleration. Okay. And then, for a period of time, it's going to travel at a constant velocity, just normal weight. Okay. Then it's going to begin slowing down, right? Acceleration would be downward. You're going to feel lighter. Okay. But then we can reverse all of this and go back down, right? So as it begins accelerating here, that acceleration is downward. You're going to feel lighter. Then it's going to travel at a constant velocity for a little bit. Acceleration is 0. And then it begins slowing down again. So the acceleration is upward. Makes sense? And these two things kind of mirror each other. So here the acceleration is upward, 0, like so. Okay? So there's 3 different cases, and they can each happen either going upward or downward. But just pay attention to the direction of acceleration, and that will indicate the net force and what your apparent weight would be. All right. Now, we can actually use if we have an actual acceleration, we can actually use that to figure out the net force and what the forces acting on an object would be in a given circumstance. So let's take a look at this. Is always a fun example to think about. So what would happen if you are in an elevator and you have the misfortune of the cable breaking and your elevator is in free fall? Okay, what would the scale read?
Wouldn't you eventually read 0
Yeah,
until you hit the ground?
right. Well, yeah, until you hit the ground, then it would
Read a lot more than 0.
yeah. So if we think about that, if you're in free fall, your acceleration is 9.8. The only force acting on you is F sub G, meaning this non-existent force there, the spring force, would have to be 0. So, yep, if there was any upward force exerting on you at all, you wouldn't be in free fall. Okay, there's that. Okay. Those are just general questions. I don't want to do that. All right, let's do an example with some actual numbers. Okay. So you have a 75 kilogram man standing on a scale. Now, why anybody would be standing on a scale in an elevator, I don't know.
For science.
For science, that's right. The elevator accelerates 2 meters per second squared upward. We want to know, what does the scale read?
$85 newtons
How'd you get that?
multiplied. Well, probably just add it. You could add your 2 accelerations and then multiply it by 75.
Add the 2 accelerations.
Right, because 2, 9.8.
Oh, so you did.
Times 75.
Okay. That would probably work. It does work. I'm going to break it down a little bit. So the way that I would process this, if we draw a free body diagram, we know he's accelerating upward. You've got F sub G and spring force, right? We know f sub g, or we can calculate it pretty easily, because that is just 75 times 9.8. I'm going to make this a little bit more apparent, the difference between those. We don't know what this is yet. That's what we're trying to solve for. Okay? We're given the acceleration, so we can use Newton's second law. Okay. We have both of those, so we can find the net force. So the net force is 150 newtons, and then I can just subtract F sub g.
Wait, but wouldn't that make him?
Oh, wait, no, not subtract F sub g. I should probably actually do that. Use the net force in this to find that. So what I would do in this case, so I would say F net equals that plus F sub g, and then I would make this like negative. It's probably the best way to do that. And then that would be negative
735.
Yeah, and then you would just add it over, which would get you 885. So, how did you reason through that? Because you just said you added,
It's 2 and 1.8.
right?
Because makes sense. I don't know.
How'd you? I mean, I'm okay with it as long as you understand why it would work.
I don't know. It just works.
All right.
If the scale is going 2.0 meters per second at a squared upward, that means he would be acting with the same force down on the scale. So you can just
Add that to the 9.8,
yeah.
and then multiply by the math. Get like a net. I mean, it works. Just as long as you are okay with the understanding of why it works and when it works. So.
Cool.
All right, let's move on.